Everybody, it's a pleasure to have Alexander Drewitz from the University of Cologne today, and he will talk about near-critical behavior of a strongly correlated percolation model. Alex?
Thank you very much, Ines, for the invitation and the introduction. So obviously, I prefer to be in South America right now, but well, it is what it is. So I'm happy to give the talk on Zoom anyways. Right, so I'm going to talk about a percolation model, which is related to the Gaussian free field. I know that some of you have already heard that talk. In particular, Ines was asking me to give this particular talk, so please blame her if you're bored. And if there's any question or otherwise that's arising in the meantime, just don't hesitate to interrupt and stop me. So what I'll be talking about is, first of all, I'll shortly recall Bernoulli percolation, which, well, probably most of you do know, but just to have like a common ground. Then I'll introduce the discrete Gaussian free field, which, again, it's probably more well known than the metric graph GFF, which I'm going to introduce later on. So, yeah, so this is ordered in terms of common knowledge decreasing, I would say. Okay, so yeah, Bernoulli percolation had been introduced in the 1940s of the last century by chemists Flory and Stockmeyer, who were investigating gelation of polymers. So one thing that you can have in mind as an example would be if you think of an egg, then at room temperature, it's essentially liquid, whereas if you start increasing temperature, it's solidifying. So in some sense, around the 50s, 60s degrees Celsius, it's starting to get more solid, and that is an example of gelation of polymers. And then Broadbent and Hammersley investigated this problem from a mathematical point of view, and they indeed did have in mind gas masks for coal miners. So the question was like, how dense can you put a porous material so that you have still air permeating through it? So the simplest model that you can mathematically think of in order to mimic this behavior or this setting would be to either think of bonds or say sides in ZD to be open or closed with a certain probability P. And this is going to happen in an IID fashion, right? So this is something that's really specific to Bernoulli percolation, where you have all this independence. And that makes the model very easy to define and, well, also, well, certainly not easy to investigate, but the IID property indeed does give you some leverage on applying certain tools. And it turns out that once you're in a dimension at least 2, you do have a non-trivial phase transition. So that means you do find a critical probability, which is denoted PC. So here, non-trivial phase transition means it's strictly positive and it's strictly smaller than 1, such that the following happens. If you choose P smaller than that critical probability, you will only find open, bounded connected components of, say, if we talk about bond percolation, open bonds. And otherwise, if you choose P larger than PC, you do find unbounded connected components. Turns out that most of them, I mean, say on ZD, there is only one, but you certainly have the existence of an unbounded connected component. So this is what the phase transition is describing, from non-percolation, which means you only have bounded clusters, to percolation, where it means you do have an unbounded connected component. So here's a picture, and what's depicted here is bond percolation. So the black bonds over here are the ones which are open, and you do open them with probability 0.4. So I mean, obviously here you can't really talk about infinite connected components. So what you can do instead, if you have this finite picture here in Z2, is you can ask, well, is there an open path that is a black path or a path of black bonds collecting the left boundary to the right boundary? And if you try to do that, then in this example, no matter where you start, maybe let's do this here, but you know, you can go a little bit and a little bit further, but at some point you'll get stuck. So you don't have a crossing from left to right. And that is not characteristic to the point on the left boundary that I was starting in, but that's a general property. So you can start anywhere in the left boundary, and you see you'll get stuck eventually, rather sooner than later, when trying to make a crossing from left to right. And the reason is that this P is actually subcritical. So P is smaller than PC for this setting of bond percolation. And so what you can do now is you can increase P. And here what you see is P equal to 1/2. And it turns out that in this particular setting, which is sort of particular, it turns out that this is actually equal to the critical probability. So that's equal to PC. And that is something that, I mean, the value of PC you can only determine in very specific cases. So usually the PC is unknown. Well, you do have positivity or strictly smaller than 1, or say certain expansions in the dimensional, but otherwise, like the exact value is typically not known. But this is sort of an exactly solvable setting. So here really you can say it's equal to 1/2, which essentially boils down or is motivated by the fact that you do have some self-duality in this problem for Z2 and bond percolation. But never mind. So now if you try to do the same thing from left to right, like finding an open crossing that is black bonds connecting left to right, you see that it's not that clear. So you can try, and you're certainly getting further than for P equals 0.4. But here you really have to work, well, you have to have a very specific, I mean, you really have to investigate to see whether you get stuck or not here. And that's actually true, I mean, due to the fact that you're at the critical point here. So then what you can do, you can increase it even further, and you see that for P equals 0.6, well, you do find crossings from left to right, and there's not, I mean, you can essentially start anywhere, and you still will, I mean, you will find a crossing that does the job. So this is due to the fact that here you're supercritical. So on the infinite lattice, you do have existence of an unbounded connected component. And this is essentially everywhere. So in some sense, this component is ubiquitous. Okay, so that was like illustrations for Bernoulli percolation. And so the gist is essentially saying that the Bernoulli percolation is rather well understood in the off-critical regime, that is either the subcritical or supercritical one. Here, what I put are a couple of fundamental or landmark results. For example, if you're in the subcritical case, it's known that you do have a sharp phase transition, which means that once you're subcritical, so you know there is no infinite cluster, you do have a decay of the probability of connecting the origin to a boundary of a ball and of radius n. So this is usually referred to as the one-arm probability, because you're asking for an arm connecting the origin to the boundary of a ball of radius n, an arm of open bonds. And it turns out that this probability decays exponentially in n. So that's due to Menshikov and also Eisenman-Baski in 87. So in particular, this also entails by summation over the spheres, over the vertices in spheres, that the expected cluster size of the cluster of the origin is finite as well. If you're in the supercritical regime, you, as I said before, turns out there is a unique infinite open cluster. So this has first been shown by, I think it was Eisenman, Kirsten Newman, and then Burton Keene gave an argument which is still very much used these days, in other percolation models also, and it's quite neat and simple. So then chemical or intrinsic distances have been investigated. So the question being here would be, if you take 2 points which are in the infinite lattice, say, let's take this one over here and this one over here, then, well, you do have the one distance between these points, that is the one norm of the difference. But you can also ask, what is the shortest path connecting them? Maybe I should take this one here. So here, okay, well, okay, I mean, this is probably not the shortest one. No, okay, I'm probably cheating here a little bit. Anyway, I mean, it's not even the shortest one, but the point I'm trying to make is that once you're in the supercritical regime, it turns out that this chemical or intrinsic graph distance is comparable to the Euclidean one in the sense that you do have multiplicative upper bounds. Also, you can ask what's the probability of finding large connected components which do not form part of the infinite cluster that's also decaying rather fast. So it's, as I was trying to make the case, this is a really well understood setting. And if you've had a look at the percolation from a math point of view, then certainly you've had a look at the book of Grimmett, and also the more recent one of Marcus Heidenreich and Remco van der Hofstad. And I would also like to make the case for having a look at this book by Stauffer and Aharoni. So Stauffer and Aharoni are actually two physicists, or were physicists. So Stauffer certainly has deceased by now, but the book is actually from the 80s. I think it's 85. This is the second edition. And it's a physics book. So you really see what physicists already knew like 40 years back, or I mean, knowing from a physics point of view, right? But it does give you actually quite a good intuition on how things actually work. And I mean, then proofs have been made precise by several articles, and also what's done in Grimmett then. But really, in terms of intuition, I would really recommend to have a look at this book by Stauffer and Aharoni. It's a nice bedtime read, essentially, if you like math for bedtime reads. Okay, so this is it, what I wanted to say regarding off-critical Bernoulli percolation. Now, then the next natural question would be to ask, okay, if you understand what's happening away from the critical point, then how about choosing P either close to or exactly equal to the critical probability? And so, as I was saying before, there's, for example, in Z2, it's known that PC is equal 1/2 if you consider bond percolation. And there is no percolation at the critical point. So that's due to work by Keston and Harris. And so also using these techniques of Schramm-Leuven evolution, which had been developed more than 20 years back, people were able, says in this setting, it's Smirnov and Werner, I think, they were able to investigate observables of that system close to the critical point. So, for example, the probability of the origin being contained in an infinite cluster is known to be 0 for P equal to PC in the setting of hexagonal or triangular two-dimensional lattices. And they were able, using these techniques, to show the behavior of this function close to the critical point. So it behaves like P minus 1/2 to some power. And this power up to a small O of 1 is equal to 5/36. And this 5/36 is referred to as a critical exponent. So the reason being is that physicists expect that observables of this type, once P approaches the critical point, they behave like power functions. So that is, they should be essentially of the type P minus PC to some certain power. And this power beta should not depend on the microscopic details of the system. So that's an indication of what's referred to as universality. So even if you change your system a little bit locally, you might get a different PC even, but the behavior close to the critical point should not change. So then this was very much planar, and in the higher dimensional setting, it was initiated by Hara and Slade in the 90s, using laser expansion in order to investigate critical exponents in high dimensions. So particularly in the mean field setting, where the percolation behavior is expected to be similar to what's happening on a tree. So this you find in more detail in the book by Marcus and Remco that I was mentioning before. So this is part of what's mathematically known. And then if you look at what physicists did, it turns out that they do know much more. I mean, knowing from a different point of depth maybe or rigor. So for example, there is what is called correlation length, which is a length scale describing and somewhat, I mean, it's inherent to the system that you're looking at. And so this correlation length psi should be a function of P minus PC. And then again, you get that it's to some power here. So the negative power should, the intuition for that is the following. So psi is a length scale that is characterizing your system in the following way. If you consider, say, you put yourself at the origin and you choose P close to PC, but not exactly equal. So for example, you choose it slightly larger than PC, and you look at what's happening around you, then if P is close to PC and you don't really look very far, but you just have a look at your sort of your vicinity, the system very much looks critical. And the question now is, well, how far in some sense do you have to look in order to figure out that you're not at the critical point, but slightly off? And this is what the correlation length is essentially trying to capture. So that means for R smaller than the correlation length, if you look at the cluster of the origin and the ball of radius BR, the volume is given by R to the capital D. So capital D is smaller than little d. I hope that's an abstraction we are fine with. Whereas if you choose R much larger than the correlation length, you do see that it's actually growing like R to the D again. So R to the small d. So this is a sign, or this is a manifestation of the fact that this here is essentially supposed to be a self-similar system. And once you're going beyond the critical, the correlation length, you see that you're actually supercritical. All right, so this is just like some physics intuition, but if you go back to what's known in math, then it turns out that it's not even known. I mean, I was talking about in the 2D case where it's known that at the critical point you don't percolate. But in Z3, this is the open problem, I would say, in percolation. So showing that at the critical point, there is no percolation. So one takeaway here is that it's hard to understand percolation models near the critical point, even more so if you're not, say, in planar or high dimensional settings. So in particular, if you're in intermediate dimensions. So here, again, what you see are some simulations, and this is making yet another indication of the fact that I was mentioning before. If you look at a cluster at the critical point, like if you consider these, I mean, these 4 pictures over here, and I gave them to you in a random order, then it wouldn't be clear which is like, you see, I mean, one is a subset of the other, but it wouldn't be, I mean, you really would have to look at the details to figure out which one is contained in which one. Whereas here, if you consider this thing here, where you have a cluster which is supercritical, you see that at larger and larger scales, things are becoming more and more homogeneous. Yeah. So on the right-hand side, there's no self-similarity, whereas on the left-hand side, where you're at the critical probability, there is. All right. Questions so far? All right. So then I come to the Gaussian free field, which is the percolation model that, or which is almost the percolation model that we want to look at. And okay, so the reason I'm defining it in this more general way is just because we can treat that setting, but otherwise you can also just think of say ZD, D larger than or equal to 3. And you can put unit weights if you like, but I'm just putting this here because this is the setting that we can still treat. And so then if you have such a graph, then what you can do is you can define a Markov chain, the transition probabilities of which are given by the weights or the conductances. So this is sort of the standard setting. And The one way, I mean, there's several ways to define the GFF, and one way is to say, well, it's the Gaussian process that is centered and has a certain covariance. Because, I mean, once you know the expectation and the covariance of a process which is Gaussian, it completely determines the law. So we can say it's got mean zero, and we also want that the covariance between 2 points is given by essentially the green function. So that means the number of visits of a random walk or of this Markov chain with this transition probability from X to Y in an infinite time accumulated. And here is where you see that we do need the transient. So if you're talking about Euclidean lattices, it means D larger than or equal to 3. Okay. So that's one way to define it. Another way to view it, which is maybe a little bit less abstract, is to say that if you consider finite subsets of ZD, it's a field which has product density with respect to Lebesgue measure, which is proportional to this expression over here. So you see that between neighbors, so X, Y should be neighbors here. That's what I'm taking the product over. You see that you have essentially this Gaussian type of behavior. And that's one of the reasons why the GFF is often referred to as a D-dimensional analog to Brownian motion, where D-dimensional now does not refer to the space, but rather to the dimension of the parameter space that we are talking about. Because the parameter space then is essentially ZD. Similar to Brownian motion, it's also conjectured to be universal. So parts of this are proven as well. For example, Kenyon showed that certain height functions of domino tilings suitably recentered and rescaled do converge to the Gaussian free field. So there's a kind of universality in this again. And also, if you compare to what we had before, like in Bernoulli percolation, I was saying, okay, I was opening, say, sides in this setting independently. And here you see that we do have sort of a strong dependence, strong in the sense that the decay of correlations is only decaying algebraically, so like a polynomial. So therefore, this is something that is well, starkly different from the Bernoulli percolation setting. So here you see a picture in 2D. So that's due to a Laurent-Coquille, and you see here that the boundary conditions. Okay, I mean this is in Z2, so you somewhat have to introduce a pinning or killing in order to make this well defined. And here I'm just saying, okay, I want the boundary conditions to be 0. And then what you see is you have this random surface, and if you now want to think of this in terms of a percolation problem, you can ask, okay. Right, I will look at those sites in the underlying lattice at which the Gaussian free field takes values larger than a certain level h. And you can also think of this as if you immerse this surface into water, or you say there's been heavy rain, then you see there's a couple of lakes. There might still be dry pieces. And the question is, can you get away to infinity starting from a certain dry piece? So is there an infinite connected component of dry sides leading, which you can follow without getting your feet wet, right? I mean, okay, this is 2D, but again, I mean, otherwise that's the heuristics that we'll consider. So you want to do that, then what you can do is you can introduce these excursion sets, which is essentially what I was just verbally explaining. So you take those, the random subset of G, for which you have that at any site in G, or in the subset, the value of the field exceeds H. Well, we've seen that there is a strong correlation in the model, so that means this percolation model will have long-range correlations, right? This is very different from Bernoulli percolation, and a priori makes things more complicated. So in Bernoulli percolation, what we did is we introduced this parameter PC. And at least on a heuristic level, this corresponds to H star now. It's not exactly the same because the H is just a level and PC was a probability, but otherwise it's the it's the parameter that makes or marks the phase transition from, in this case, we are asking how small can we actually choose the level such that the excursion set, which is getting bigger and bigger as I decrease h, still doesn't percolate. And this has been introduced as a percolation problem by Leibowitz and Saleur in 86, so 40 years back. There has been a follow-up paper by Brickmont, Leibowitz, and Saleur, where they proved certain parameters, certain properties of H star. So then you see that for a long time, nothing has happened. So until Pierre-François Rodriguez, together with his supervisor, Alexandre Snittmann, in Pierre's thesis, they investigated H star further, so they got more refined results. And the reason for this gap in time and for the fact that it happened in 2013 or around that time was that they were actually taking advantage of methods that Alessandre had introduced for random interlacements, which is very much related on the one hand by the correlation structure of that model, on the other hand via a so-called isomorphism theorem, which allows you to transfer going back and forth between the two models. So that is the reason why this happened around that time. So Snittmann, he introduced that model around 2010 or 2007, like 2007, and then that gave rise to new techniques. So anyways, so together with Alexis Prévost, who was my PhD student at the time, and Pierre, we investigated this here further, also in a follow-up paper with different critical parameters. So, for example, what we showed was there is a phase coexistence. So that means if you choose H, I mean, there is a certain level of H such that you do percolate above H and you do percolate below H. So this phase coexistence is something that is interesting from a physics point of view. And for Bernoulli percolation, that had been proven by Campanino and Russo in 85 already. So then people were also interested in sharp phase transitions. So that is what I was saying before regarding the result of Menshikov. So the exponential decay in the Bernoulli setting. And this has also been established for the GFF. So there's, first of all, so this is Pierre-François with Hugo de Meneux-Copin, Franco Severo, and Subhajit Goswami. And right, so they proved it for the GFF. And then, so Stephen Moorhead was actually after this one. So I think this is the preprint year, but he proved it for a more general model, including the GFF. Okay, so then there has been investigations on critical parameters for this thing on trees. So here that's Arbecherli Snittmann. This is Alexis Prévost with Joël Gaillot, who is another PhD student of mine and myself. This is Czerny Locher, I think. So I'm not giving all the results, but just trying to make the point that this discrete GFF has in fact been intensively investigated and results have been obtained. So what I'm focusing now on for the remaining part of the talk is a model which a priori looks more complicated. So you would ask, why do you introduce it in the first place? And it turns out that even though it's a little bit more complicated to introduce, it offers a lot, somewhat it adds a lot of integrability to the system. So what we are doing here is the following. So that's something that's going back to, so this here, it's not Varadan, it's Varopoulos. And he introduced this in 85 already, which essentially is the following. So what we're doing here is we have our lattice, right? So think of this as a subset of Z3. And what we are doing now is we just add cables between neighboring sites. So what we do is, It's just line segments. So this thing becomes what people refer to as a metric graph. So here it's continuing and so on. Right? I mean, it's really as simple as this picture looks. So you're just adding line segments between neighboring vertices. And then what you do is you, well, you start with your discrete model. That is, you sample your GFF on, on the vertices. And then the next thing is you interpolate. So what you're doing is, you got your field, say, at this vertex and at that vertex. It takes values phi x and phi y. And you extend the field to this cable system now by saying, well, I'm adding, or like from on this line segment, the field behaves like a Brownian bridge going from phi x to phi y. Okay, so this is what we are doing here. And as I said, it looks a priori a bit more complicated. And then what you say is this induces a bond percolation problem. So in the following way, we say that an edge is open if and only if, or say whether, I mean, conditioned on the values of the GFF on the discrete lattice, with this probability here. And this, it turns out, it's just the probability that the Brownian bridge from phi x to phi y stays above this level h. Okay, so do you have any questions regarding the model or this cable system? Because I think it's important that this is clear, since otherwise you might get lost.
Just a question: does this the correlation function of this thing corresponds to the Brownian motion of this on this cable system, or?
So yeah, you say. So you can. So if I get your question correctly, you're asking whether, say, if you take
like your graph with the edges, it's a metric space, like a continuous metric space.
Yeah, exactly. Right. Mm-hmm.
So yeah, okay. If you define a Brownian motion on it with some rule on the
exactly.
Okay.
Exactly. Yes.
Okay,
so yeah, this is exactly true. So what you can, I mean, before we said, okay, before we said that the correlation function or the covariance of the field is given by the green function of the Gaussian free field of the simple random walk, and you can suitably extend this to saying that for this field that you have now on this metric graph, it's you can essentially say it's the green function of the diffusion that's living on this cable system if you define it correctly. And the correct way to define it is right. I mean, as long as you're on this line segment, it's just like a one-dimensional Brownian motion. And so heuristically, once you get to a vertex here, you can say, well, for Brownian motion, what you have is you have your decomposition into excursions. So then what you do is you can say, again, intuitively at least, for any of the excursions, what you're doing is you're choosing one of your 2D directions uniformly, say, okay, that's the one it's going. And then at some point, there will be a first excursion that is long enough so that you actually do hit one of your 2D neighbors. And from there, you continue the same thing again. So it'll behave like here, it's like a Brownian motion on this thing. Then it's getting here to this vertex, say. And then you can say, okay, you have a look at the excursions, which go like this. And at some point, there will be a long excursion, say like that, and you'll hit your next point. And then, exactly. So the covariance of this extended field is then essentially the green function of this diffusion of the cable system. Further questions? I don't see any. So what we do now is what we did before twice already, right? We want to investigate this thing now for from a percolation point of view. So we want to investigate observables. And bear in mind, we now talk about this bond percolation model, right? So we say a bond is open if the entire Brownian bridge, say, going from this one to this one, if this on this entire line segment, it's not dropping below H. So we can all define all these respective quantities again. We got the excursion sets. That is the, well, now, so usually what I'm doing, I put a tilde if I'm talking about the cable system quantities. So if I don't forget at least. So that means here we have this subset of the cable system at which phi takes values larger than at least H. The cluster of the origin in this excursion set. And what we do now is by theta tilde H, slightly reversed to the previous, we say it's the probability that KH is bounded. I'll get back to this. And again, you can define a critical parameter, and then you can ask how small can you actually choose this parameter so that the probability of it being bounded, or the cluster of the origin being bounded, is still 1. So the probability of percolation vanishes. And we also consider, similar to what Menshikov did for Bernoulli percolation already, the radius function and the 2-point function. And here we consider the truncated versions. So this essentially helps you to be able to treat the supercritical and the subcritical case at the same time. So if you think about, say, to connect the origin to the boundary of the ball of radius n, but you don't want to do so in the infinite cluster, but sort of apart from it. So we were not the first to investigate this, and in fact, so here credit goes to Lupu, that is Titus Lupu, who in his thesis was investigating this model, and so he already obtained that at h equals 0, he obtained an explicit formula for the 2-point function. So that is the probability of connecting 0 to x in your cluster, in your sign cluster, if you want. So that is, you only take those elements of the cable system which at which the field is taking positive values. So he got this formula here, and in particular, what you see if you take x to infinity, this behaves like a distance to the 2 minus d. So again, this is the same as the decay of correlations that we have in the model. And it also tells you, just using a little bit of erudicity, essentially, that you do not percolate at 0, or say above 0. Because if you did, in some sense, you would have a positive density of the, like a point being in the infinite cluster. And if you take 0 and x far away, it should essentially converge to some positive quantity bounded away from 0. Because essentially you take 2 random points and ask what's the probability of them being in the infinite cluster. Okay, so it would each be positive, so the product is positive, but here you see it's decaying to 0. So that means you cannot percolate above 0. So therefore, what you get is that h tilde star is certainly non-positive. And you don't percolate at 0. So this we should keep in mind. Maybe let me...
There is something I found mysterious in your formula. You're not on ZD anymore? I mean, why is G0, 0 and GXX? Why are they 2 different things?
No, yeah. I think... so I think Titus was already considering, so I do not remember exactly if he considered ZD for this. I think he treated more general settings also. I mean, you're right. As long as we are on ZD, these are certainly the same, right? But otherwise, it might be that they're different.
Okay, thank you.
But this is maybe as a remark already, later on we will consider sort of general graphs, but what we always need is some kind of green function regularity. So we don't want, we want that these guys don't explode or don't go to 0. Some certain, uniform boundedness. Okay, so then it was Jian Ding with his student Matteo Wirth who in 2018 considered the setting of the z tilde 3, and they showed that the radius function, so the one-arm probability, essentially behaves like r to the minus 1 over 2, up to possibly a logarithmic correction over here. So again, you see that, you get this exponent here, which you've seen in the physics heuristics before. And you get the logarithm, and then, usually what you ask is, you would expect that one of the two might be the correct thing, right? Either the r to the negative 1/2 or the r over log r to the negative 1/2. So I'll get back to this, but for the time being, a couple of years back, this was state of the art. And so one thing that we will need in our results, and it's not just that we need it, but this is just a crucial quantity in investigating this GFF business, is the capacity. So capacity gives you a measure of a set, which is different from, say, volume or surface. But in some sense, capacity is measuring the size of a set from a point of view of a Brownian motion or a random walk starting from far away. So you can behave that essentially it behaves the probability of a random walk starting from far away, hitting a ball of radius r or whatever set you have, is of the order r to the 2 minus d times a certain constant, and the constant is essentially the capacity over here. So the capacity gives you the size of the set in terms of hitting probabilities. And one way to define it is by saying you're using just the escape probability. You're just summing the escape probabilities of your set K. So here you can only escape if you start in the boundary of a set, and these are the return times. So the probability of never returning, you sum it over the boundary of your set, and then you can argue a little bit using reversibility by saying, okay, this is similar to random walks coming from far away hitting your set. In particular, the asymptotic behavior of large balls. So for large balls, the volume would be like r to the d, surface would be r to the d minus 1. Capacity turns out to be r to the d minus 2 if you're in ZD. So it's growing slower than, say, surface or volume order. And so what we did together with, again, Alexis and Pierre, as I think everything that's coming from now on, is we investigated the law of this random, of the capacity of the excursion set of the cluster of the origin at level H, right? So this was the cluster of the origin above level H, and it turns out that the right way to measure its size is in terms of capacity. And for this capacity, we can show that it has a density, and that density is turns out to be explicit. So this is the expression that we get. Less maybe than even the explicit value of it is, for example, the long-term, large T behavior that you might be interested in. For example, at h equals 0, where you see that the exponential decay vanishes, and you're just left with something that's decaying like t to the minus 3 over 2. All right, so we have this law of the capacity, and what can you do with it? Well, for example, you get the following. So first of all, we can show that the probability of this here was the probability. Maybe let me give a sketch here. That was the probability of non-percolation, right? So the probability that KH is bounded, and okay, this is maybe a bit too. So what you have here is here we put H, and here we put theta tilde of H. And it turns out that I was already saying before, you don't percolate above level 0. This is what Tito's proved. So if you put 1 here, say this is 1, then we know that certainly we don't percolate, so the probability of KH being bounded is equal to 1. Now what we show is that this probability is actually given by this expression over here, where phi t is just the probability that a Gaussian with mean 0 and covariance given by the green function is smaller than or equal to t. So you see that h equals 0 gives you just 1/2, so twice 1/2 is 1. And you can also get from this immediately that the behavior close to the critical point, which is h tilde star equal to 0, is linear. So it looks like, say, okay, so what we have even the slope, so I'm not going to manage to do this, yeah, but and then it's going to 0. So in particular, the picture over here, close to the critical level, which is h tilde star, is linear. So maybe let me emphasize this once again. I was mentioning before that in the Bernoulli setting, there are a couple of cases where you do know the critical value for percolation. That is either, well, you know it on trees, you know it in the planar setting, but in general, it's not known. So here it turns out that in our model, in really very many cases, essentially all graphs that you can naturally come up with and that fall into the setting on which I was able to define the model, that is the transience assumption, you do get that the critical parameter is exactly equal to 0 and that you do not percolate at the critical point. And we get that the critical exponent is equal to 1, that is close to the origin, close to 0. The non-percolation function is behaving linearly. So it was, maybe let me show it here. So you can come up with examples where the critical parameter is different from 0, but you have to work a bit for this. And that's really what Alexei also did in his thesis as one of the many things he did. And yeah, so I think this is on the one hand quite nice and also somewhat surprising at first glance, at least, that this h tilde star does not depend on anything really. Like, for example, on any Euclidean lattice where you put your cables, it's always equal to 0, right? And for Bernoulli percolation, you know, okay, it's behaving like PC is behaving like 1/2D in first order. So, I mean, there certainly is a dependence on the lattice dimension, which is not present here. Okay, so the assumptions that I'll be working on from now on are regular volume growth. As I was saying, green function regularity, this is sort of a technical thing, uniform ellipticity. So in particular, we include the cases of Euclidean lattices. We use alpha because people who were investigating heat kernels on these kind of graphs used alpha and also nu. So we took it from them, and yeah, you have to bear with it for the time being. So in particular, I was saying nu, the green function decay in our setting is alpha -2 or d -2. And we also can cover things like, for example, this so-called Toblerone graph, where here you see that, I mean, this is just a finite subset, but you should think it's extending in the two-dimensional and also the cross Z thing. So here you have a Sierpinski free gasket, and you take the Cartesian product with Z, and then, you know, if you're in Switzerland, you would call this a Toblerone graph. Okay, so this is how the name came up. So we can use or can cover these prefractals as well. So I was talking before about this notion of correlation length with which, you know, I gave you the pictures and the physics intuition that it's essentially the length scale which you have to go in order to figure out you're not at the critical point. And what we do is we choose this psi h and we set it, well, I mean, we're free to choose something and then show that it's actually a sensible choice for this correlation length. And So we define it in this way, nu being the thing from the green function. We know h tilde star is 0, so that means we end up with this expression over here. And what we get is the following. So what we need here is a nu strictly smaller than 1. That means just a little bit smaller than Z3, say. We got other results also, but the strongest ones we find in this setting. And what you see is the following. So here you have a look at the radius function. So you ask what's the probability above level h to connect the origin to radius r. And now the thing is that if you choose the radius a little bit smaller than the correlation length, then what you see is that this thing here and this thing here, they don't really kick in. So r over xi is very small, so that means these two exponentials essentially are negligible. So you choose r smaller than the correlation length, meaning you're only looking as far as to not observe that you're not at the critical point. And there it turns out that if you don't look far enough to distinguish from the critical point, it turns out that you can get away, like these one cancel or essentially cancel. And you do see that, in fact, you behave as if you were at the critical point, because we know 0 is the critical level. So these are the critical 2-point functions. Now, once you go beyond xi, that is, you choose r much larger than xi of h, you see that these things here are sort of negligible. And what is really making or sort of being responsible for the decay are these exponential things over here. So you see that once you go beyond this correlation length, you do see stretched exponential decay of the of this 2-point, not 2-point, but 1-arm probability. Okay, so this is sort of reminiscent of more quantitative, but you do see that this is sort of completing the picture in some sense between critical and off-critical regimes. Okay, so what is this? I think that's the same. We can get further critical exponents. For example, the volume critical exponent, which you get as follows. So you define the volume of the cluster of the origin, again, conditioning or restricting to bounded clusters in case h is negative. Okay, again, that's supposed to behave like a power law. So you can take logarithms and divide by log h and get a power gamma. We get that this gamma actually exists. So existence of critical exponent is also something that in the general setting of Bernoulli percolation is not known, apart from the special settings I was mentioning. And we get that it's related to the other critical, or to alpha and nu. That is the volume growth and the green function decay, or also you can define it in terms of other critical exponents. So you'll see it in a minute, maybe, which is clearer. And also, just as a short aside here, as an indication of the rotational invariance of a putative scaling limit, we get that the logarithm of these two, that is the 2-point function, in a certain direction e, does actually not depend on e. So at least the bounds we get here, if you choose eta small, there is no influence of this e coming in here. So in that sense, you expect that in the scaling limit, you get some kind of rotational invariance. So here, that's a little bit of a cheat sheet. These critical exponents that I was mentioning, they're not sort of independent of each other, but there are relations, right? I was saying, okay, if you take the 2-point exponent, you got it. And if you sum over spheres of a certain radius, then that should give you some kind of indication of what's happening to the volume critical exponent. And this is manifested by so-called scaling relations, which give you the relations between different critical exponents. or hyperscaling relations, which are only, I mean, they are sort of more speculative. And what we get here, so what I try to put red is the ones that we can actually compute, the critical exponents. So the exponents are given here. We already saw a couple of them. I'm not going to define them all, but we have seen beta, we have seen gamma, we have seen nu c. And here, I mean, if you've seen critical exponents before, this might help you a little bit on recalling which one was which. So we get the ones which we have in red over here. And if you compare to Bernoulli percolation, okay, the only point or the main point I'm trying to make with this is that in Bernoulli percolation on Z3, everything is wide open just because you don't even know whether you do percolate or not at the critical point. So here the approximate signs indicate that all of these are simulations, okay? Okay, so okay. One thing I want to emphasize here is which I mentioned before. You see that, I mean, here what's showing up is essentially alpha and nu, and alpha and nu are macroscopic quantities or macroscopic parameters, right? One was the volume growth, the other one was a green function decay. So that tells you that if you mess your graph or perturb your graph a little bit, that does not change anything on the critical exponent. So that's fitting into this paradigm of universality. So we also see that if you take alpha to 6 from below, which corresponds to taking nu to 4 from below, whatever that means if you don't want to go along integers, but you can make this precise because you've seen, I mean, these Toblerone graphs, for example, they also had some kind of intermediate dimensions which were not integer. So then what you do recover is in the limit, the mean field values for Bernoulli percolation. That is from dimension 6 onwards, which is the upper critical dimension. You get that the critical exponents of our model do coincide with that of Bernoulli percolation, whereas below the upper critical dimension, they do not. Ines, how much time do I have left? I see that
I think we started a bit late, so maybe a couple of minutes.
Okay, so yeah, so here, so here what I'm trying to make is a sketch of like ideas on how to find bounds for this 2-point function, not 2-point function, but radius function. So there's essentially 3 steps in here, and I won't be able to give the details, but maybe you can take away a little bit of the intuition that's behind. So the first step that we are doing so what we want to do is we want to make a connection from the origin, which is this one over here, to the boundary of the ball of radius r, which is somewhere around here. And we use different objects. So first of all, what we do is we explore the cluster of the origin up to the correlation length. So up to essentially, sorry, in a ball of radius psi. And so with reasonable probability, you do actually touch the boundary of this ball in the excursion set kh tilde psi. So that means you can make a connection up to the correlation length. And then the next step is to consider an isomorphism now for sort of a modified graph, because you already explored this thing over here, between the Gaussian free field and this model of random interlacements. So the model of random interlacements is connected to this GFF. And if you think about interlacements from a percolation point of view, then interlacements itself is maybe a little bit boring. because it's super critical no matter what what the intensity U is. It's always an infinite connected set. But this turns out to be rather helpful in our setting because we know that we want to use U small. And this thing here is big enough for one of these interlacement trajectories to hit this, this cluster here of the origin. So that means we can make a connection from this cluster up to correlation length to something that's further away. And so once we are actually further away, we can say that what is happening here is sort of independent of what we have explored over here. And again, what we are doing here is we find a consecutive sequence of balls. These balls should be large enough so that the interlacement process on these balls is showing some property which is called local uniqueness. So that means we can, by using pieces of trajectories, make connections along these balls that at least extend to this ball or boundary of the ball of radius r, and patching these three things together. So first of all, the exploration of the cluster up to correlation length of the origin, the green interlacement path, and then these balls along which we propagate the connection. This altogether, if you use the isomorphism, gives you a connection to the boundary of the ball. I mean, okay, this is intuitive and not very rigorous, but this is really what's happening behind. So maybe to conclude, let me just mention that this subject has been very well investigated recently. On the one hand, that's nice. On the one hand, so CD is John Ding and a student of his, so competition is tough. So anyways, what I'm saying is here we had a look, or I mean, actually John and Tsai, they had a look at this one arm, the one arm probability in the mean field regime, right? So this is alpha larger than or equal to 7. They showed that in fact, from then on, you got it independent of the dimension that it's decaying, like r to the -2. Ganguly and Nam proved the Alexander Orbach conjecture, or type of it, in dimension larger or larger than 20. So that essentially tells you that the spectral dimension of the random walk is 4/3. So that describes the decay of the heat kernel on the critical, on the IIC. That is the critical cluster condition to be infinite, which has also been constructed in the meantime. So then, coming back to what I said at the beginning, so there was in 2018 there was a John Ding and Matteo Wirth. So now there's John Ding and another of his students, and so around the same time we got to similar results. That is that the decay of this one-arm probability is actually governed by this n to the -2 nu/2. So in Z3, this means n to the -1/2. So the logarithm that John had in his first bound is actually not the right, but we just get this polynomial decay. So there's a couple of papers which, I mean, this one appeared first, then half a year later, these two appeared around the same time on Archive. I think we were one day before, but so we got more general graphs, but John and his student got more general dimensions. So I'm happy for all of us. Yeah, okay. So, and okay, there's further estimates on the volume of the critical cluster. So this should be H. Sorry, 0. And there should be a tilde here. Oh, okay. So anyway, I'm trying to make a case that this is still very much going on and in progress. Yeah, and so hopefully I convinced you that this is a nice model, or maybe if not a nice model, it's a very useful model because it gives you some intuition on what you would expect, and not only what you expected for this model, but so we did some simulations together with a master student of Pierre, so that's Chris Charloup, and then again Alexis, Pierre, and myself. For models with a similar decay of correlations, so that is the simple random walk on the torus, well, also for the discrete GFF, which up to now we're not able to treat, cable system we were able to treat rigorously. And it turns out, I mean, you would expect similar, I mean, you would expect that this is due to Weinreb and Halperin essentially, that the universality class that your model falls in should essentially depend on the decay of correlations in that model. So, I mean, we are certainly happy that we can solve this one in some sense, but obviously the question is, how about other models? What can we say? And so far, the answer is not much. So, yeah, maybe this is kind of motivation for some of you to have a look at this if you want to make some progress. And yeah, with this, I would like to thank you for your attention. And yeah, thank you very much.
Okay, thank you, Alex. Questions?
Alex, Paulo here. I got lost how the random interlacement entered in the Gaussian free field in the cable.
Yeah, okay. So first of all, there is. So maybe what's maybe what is mostly known, or I guess most people maybe know this thing that if you take the GFF squared and times 1/2, that's equal to the loop soup at level 1/2. So this here is a Brownian, well, I mean a random walk loop soup.
Yeah, I know that, but this is a mysterious relation, right?
Yeah, I agree. I mean, still for us, they're mysterious as well, right? You're right. I mean, it's mysterious. You do generating functions. Yeah, so that's another thing. I mean, it would be nice to find proofs without mystery, I guess. But so from this, what you can do is you can interpret random interlacements essentially as some kinds of Brownian loop soup or random walk loop soup coming from infinity. And so if you have a look at the local picture and you tune your level, so you increase the level, and you take the point further and further away, then you see that there's, you get some local picture in which this is interlacements. So essentially from that, you can get that there is an interlacement, isomorphism between the Gaussian free field and this interlacements model. And this actually extends to the cable system also. And this is one of the reasons why we need this Brownian bridge. So you might ask, okay, why a Brownian bridge? Why not something else? But we need the Brownian bridge for the isomorphism to still hold true if you extend both. That is first the random interlacements, which, as Hubert was saying, I mean, you instead of random walks, you look at diffusions. And then you still recover sort of a similar isomorphism, which Tito had improved, in fact. So then, I mean, here you see that one of the problems is that here you got this square. So you can't really say anything on the sign, but by the introduction of these cables, you get a continuous process. So therefore, if you have a sign switch, you must have a zero of your process somewhere. And that's something that you can only discover by saying you have a look on a continuum domain of definition instead of a discrete one. And this is sort of where Tito started off and then said, okay, you can actually show that the signs are IID, and then, yeah.
Okay. Thank you, Alex.
You're welcome.
More questions? Okay, so if there are no more questions, let's thank Alex again.
Well, thanks for having me.
Yeah, and we meet again next Wednesday, I guess.